Hello scientists, this is Miss R, and today we're talking about Lab 5.06, Springs, Kinetic, and Potential Energy. We have a couple state standards that we're addressing. I'll let you read. The first part of this lab is to watch a 2-minute video. It's a little goofy, but you might like it. This is what the video screen will look like, and it's just 2 minutes about elastic potential energy and kinetic energy. This, of course, is elastic potential, and this is kinetic. So when it's stretched, the rubber band has potential energy to snap back, and when it's in the process of snapping back, it's got kinetic energy. Once you've answered these, watched the video and answered these 3 questions, you can move on to part 2, investigating elastic potential and kinetic energy in springs. The first thing you want to go to is the simulation for masses and springs. When the simulation first pops up, there'll be a yellow play triangle in a window that looks like this. Just hit the play triangle and it should pop right up. Let's just do a little bit of a tour about the simulation. There are 3 springs here. One of them you can adjust the spring constant on, the softness or hardness, or how hard you have to pull on the spring to deform it. In rubber bands, it would be like the skinny rubber band versus a big thick rubber band like you have on broccoli. That would be the difference in elastic potential of the spring. And you can do that here. So this spring you can adjust. These 2 springs have fixed spring constants, and we can kind of see what that means here. It's basically how stiff it is or how hard it is to make this spring stretch. And we can measure that in a specific way in the lab. Let's show how you can change the potential of this spring. So you can make it really hard to deform, or you can make it really soft, like a slinky. We'll put that back on medium and take the mass off. These masses we know the weights of, or we know the mass of. These masses are unknown, and it will be our job in the lab to find the mass of these springs using a formula. One thing that we want to measure in this lab is displacement. That's how far the spring stretches. And we can do that by taking this ruler here, putting the 0 at this dotted line, and then we can take a mass here and hang it. And when it stops bouncing up and down, we can measure where this little attachment point here is on the spring, and we can see it's right on 10 centimeters here. So the displacement of this spring would be 10 centimeters. All right, let's go back to the lab now. So our first job in the lab is to find out where there is 0 potential energy, 0 elastic potential energy. And if you're wondering how you figure that out, there's a little bit of a graph. We can click here in the simulation, and it says show energy of, and we get a graph in the simulation that looks a little bit like this. If we want to see the potential energy of elasticity, it's this turquoise bar here, and you can see they add up all the different kinds of energy here for a total energy bar. So it's your job to put a spring on, or put a mass on the spring, and watch this graph here to figure out when potential elastic energy is 0. So in the simulation, we want to do show energy of spring 1. Here's the graph that will appear. And don't worry if nothing appears yet. We need to put a mass on there. And you can see now we have some potential energy due to gravity. In other words, this weight can fall, so it has potential energy to create kinetic energy as it falls. It doesn't have any elastic energy because we haven't pulled the spring out yet. So we can watch the kinetic, the potential elastic, and the potential gravity to figure out when there's zero elastic potential. We'll just give you a hint here. In the next question, we have to figure out why we used varying conditions. We may also want to test this with a different mass. You can see all of the energies are different here. Let's do it on spring 2. Just see, oops, we got to show the energy of spring 2 then. Let's try that again. So also be noticing when the kinetic energy is 0, because that's one of the next questions in the lab. Why do we have to use varying conditions to test when elastic potential energy was 0? And also, why do we have to use those varying conditions to figure out when kinetic energy was 0? Let's just see if a 50-gram mass makes any difference. And pull it way down. And this green bar here is the Ke, that's kinetic energy, so you'll need that a little bit later for the next question in the lab. So, by investigation, determine when elastic potential energy is 0. Make sure you test your idea with several masses and all 3 springs and vary the stiffness of spring 3. I will let you do that. We kind of looked at spring 1 and spring 2 with a couple different masses. You can look at spring 3 and try varying the spring constant here. Make sure you click on show the energy of spring 3 and then play around with the spring constant or the softness. Think about why we used varying conditions, and then you're also prepared to do number 6, which is finding out when the kinetic energy is 0. Make sure you're looking for the green bar here and figuring out when that is 0. For number 7, we want to put a mass on the spring and observe the total energy graph as it oscillates. The total energy graph, remember, is all the way to the right. It'll look like this in the simulation, where it says total. And it's adding up all the kinds of energy in the graph. Pay attention to the details of the energy distribution. In other words, when is there a lot of kinetic energy in the total? When is there a lot of elastic potential? And when is there a lot of potential due to gravitational position? Like basically, if I take my mouse and pull it up here, it has more energy of gravitational position because I can drop it further than if I hold it down here. So if you've got a mass on a spring that's up, it has more energy of position than if it's down. Down meaning closer to the Earth's surface, where gravity has acted on it. So think about why energy is distributed differently for several situations. For example, when is there only kinetic energy? What makes the elastic energy increase? Make sure you test your idea with varying conditions. Write down what you think the relationship is between elastic potential, in other words, stretching that spring, and kinetic energy, that spring moving. When you're working on question 7, here's a few things you might want to think about. Obviously, you want to use varying masses, but we'll start with 250. When it's just sitting there, is there any kinetic energy? If you look at the total, on the very right-hand side of the graph, it's all blue, which means it's all potential energy due to gravitational position. As you drop the weight and it starts to stretch the spring and it moves, you get some kinetic energy. And as the spring deforms, as you stretch that spring, it's got more potential, elastic potential energy. In other words, the energy of stretch that is going to snap back. So this is, this rubber band now has elastic potential. If I do this, it doesn't have any elastic potential. In the process of going from lots of elastic potential to none, when it's moving, it's got kinetic energy. That's just a bit of a hint. Let's drop it again and see how those different kinds of energy change as the weight bounces. So here's kinetic energy in the beginning. Keep an eye on that. Look at potential energy due to position or gravitational potential energy. Here's elastic potential, and here's thermal energy. Some of the energy as the spring is bouncing up and down is turned into heat because the spring experiences friction. So some of the total energy, it seems like it's lost, but it's just going out into the environment, and we can't find it. We could set friction to none here. And you can see there's no thermal energy here because now we're living in a frictionless world, which would sort of be nice, except when you have to drive. So for number 8, we're going to consider a different system with potential and elastic energy. We're going to go to a skate park simulation, and we'll look at that. Make sure you check bar graph in the upper right hand corner, and we're going to look at the energy distribution as a skateboarder rides a ramp and contrast that to the mass moving in the spring. So we just looked at the graph of the total energy in question 7 in the masses and springs simulation. Now we're going to go look at the relationship between potential and kinetic energy in a different situation and compare it to masses and springs. So when you click the link in the question, you'll get a screen that looks like this. You just want to click intro here. You'll get a simulation that looks like this. You want to click bar graph. I know you might not be able to see it in the screencast, and that's okay. We're going to put our skater on the ramp here and watch the graph over here. So again, I clicked bar graph, and I have a bar graph over here. Let's get this skater moving. Let's get her up the ramp a little bit. Oh, look, her potential energy is greater when she's up the ramp with potential to fall down. That's how I think about potential energy due to position. As she starts to skate back and forth, her kinetic energy increases and her potential energy changes, and I'll let you make some conclusions about the relationship between the kinetic and potential energy and compare that to what we saw in the masses and springs. The first part of the next task in the lab is to watch a video on Hooke's law, which involves how to calculate the spring constant or the softness or hardness of the spring, how difficult it is to deform or move. It's quick, it's only about 2 minutes, so I think you can handle it. It does involve a little math, but you're smart people. So once you've watched this really short introduction to Hooke's law, or if you feel like you need a little bit slower introduction with a little bit more detail, you can watch this video. So it's your choice. Watch one of them. Explain what the formula for Hooke's law is and what the K in the formula represents. And describe an experiment in which you find K for the spring. I guarantee you it's in the video. You're smart people. Explain what variable would you change and what would be measured in the units you would use. It's all in the video on Hooke's law by Doodle Science, the very first one here. In the moving on, we have some explanations of things you need to know. Here is something that might be helpful in the questions earlier. This formula will be helpful in a little bit later on in the lab. What we're going to do now is determine the spring constant. We're going to use Hooke's law and rearrange it a little bit so that we have the spring constant on the left-hand side, and we basically divide both sides by x here, do a little algebraic rearrangement. And so the formula now is K, the spring constant, is equal to the force divided by the displacement, or how much that spring stretches. And we'll measure that with the ruler. So what we're going to start with is finding the spring constant of spring 1, that spring on the left, by figuring out the force in newtons, which we can figure, which is the weight, basically how much gravity is pulling on the mass. And I'll show you how to calculate that in just a minute. It's just 9.8 meters per second, the acceleration due to gravity here on Earth, times the mass in the spring in kilograms. So this is why over here, the mass, instead of being listed as grams as it is in the simulation, it's listed as kilograms. So this is 50 grams, this is 100 grams, this is 250 grams. So you multiply this number by 9.8 meters per second to get the force in newtons. The displacement we'll have to figure out here in the simulation. So here are a couple of things to think of when you're taking your measurements. Here's the 50-gram mass. I'm going to put it on here and let it bounce a little bit. I'm going to make the graph go away so it's not distracting. So I'm going to say show energy nothing. I'm going to make sure friction is in the middle. If we have no friction, this will just bounce forever. So if that happens to you, just slide your friction into the middle. I'm not going to mess with the softness because that's spring 3 and we're simply concerned about spring 1. So I've hung 50 grams on here. That's the first mass we want to take measurements for. I put the ruler so the 0 is on this dotted line. And now I'm going to measure where this part of the spring is, since that's what's at 0 here. So it looks to me like it's at about 4.5 centimeters here. So let's go back and put that in our table. Okay, this is the part where you need to get out your calculator or your handy-dandy cell phone, as the case may be. You need to multiply to figure out the total force, the acceleration due to gravity, which we know here is a constant on Earth. It's different on other planets, but on Earth it's 9.8 meters per second, or per second squared, times the mass in kilograms. Remember, we were using the 50-gram spring, which is 0.05 kilograms. I multiplied 9.8 times 0.05 on my calculator, and I got 0.49 newtons. Now we can go up here where we've rearranged the Hooke's law formula to K, or the spring constant, is equal to the force, that's this box here, divided by the displacement. So all we have to do now is take this number here, our force, and divide it by our displacement right here. We'll make that another color. So force, 0.49 newtons, divided by displacement, 4.5. Oh, I need to put that in meters. So I need to divide 4.5 centimeters divided by 100 is equal to 0.045 meters. So I converted it to meters because this is in meters per second, and we want those meters to cancel out. So 0.45 meters is equal to, now I just want to take 0.49 and divide it by 0.45. And I get 10.88 as a spring constant. I will let you guys do the rest. Remember, you want to convert your centimeters of displacement to meters of displacement. We'll go through that calculation one more time. So use the mass of the mass multiplied by 9.8 meters per second to get the force. That's what's in yellow here. Then take the centimeters, the displacement, what you measured with the ruler in the simulation, how far the spring stretched once the mass came to a rest. Divide the centimeters by 100 to get meters. And then take this box here and divide it by this box. Or take the force and divide it by displacement to get the spring constant, as shown here. K is equal to F divided by X, the displacement. F, in this case, is the force being applied to the spring due to gravity pulling on that mass. So for the next part of the lab, now that we know the spring constant of spring 1, because we calculated it earlier, we're going to be able to use that spring constant to figure out what an unknown mass is, how many grams an unknown mass is. Those red, green, and yellow masses, we're going to put one of those on spring 1, measure how much its displacement is, and we'll figure out what the weight is, and we can figure out the mass from there. And I'll explain all this math here. We'll go to a screen where we can do a little bit of algebra. So let's do a little algebra here. So we know that this is the basic formula for Hooke's law. The force in newtons is equal to the spring constant times the displacement, or how far the spring stretches when you put the mass on it. We know that we can calculate force by multiplying 9.8 meters per second squared times the mass in kilograms. We did that in the last problem. So F can be replaced by 9.8 meters per second times the mass. Got a better 9 here. Times K times X. So we're trying to find the mass here. So if we rearrange this formula a bit, we can find the mass by dividing both sides by 9.8 meters per second. So let's do that, because the rules of algebra say we can always do the same thing to both sides of an equation and it will still be equivalent. So now these cancel out and we get mass is equal to the spring constant times the displacement, remember that's in meters, not centimeters, divided by 9.8 meters per second squared. So let's use that to find one of the unknown masses. So in the simulation, we're going to find out the mass of these cylinders that don't have the number of grams marked on them. They're of an unknown mass. We're going to put one of the cylinders here, and we need to measure the displacement in order to put that in our formula. So here's 0, and it looks like the displacement's about maybe 6.5 centimeters. So we'll convert that to meters and put it in our formula. So far we have one of the things we need to calculate mass. So we know that mass in kilograms, of course, is equal to the spring constant, which we found out on our sheet. We'll go look at that in just a second. For a moment, though, we know that we have 6.5 centimeters that we measured in displacement for the green spring. And we want to divide that by 100 centimeters in a meter. And that all works out to make 0.065. I'll have to squish it here, meters. So our displacement that we just measured, we found by experiment, is 0.065 meters. We just converted centimeters in the simulation to meters, and that's our x. So our displacement that we measured in centimeters with the ruler, that's x. That's the displacement. That's 0.065 meters. It's 6.5 centimeters divided by 100 to get meters. So we'll put the displacement here, 0.065 meters. We'll put divided by 9.8 meters per second here, second squared. And now let's go find that that K, that Hooke's that spring constant from Hooke's law we used in the. So in the previous problem, we calculated the spring constant to be 10.88. If you found something different, use your spring constant. So here is the spring constant that we need to put in our formula. So back to math land, and we're going to put our spring constant K in here, 10.88, and then use your calculator to multiply 10.88 times 0.65 and divide the remaining number by 9.8 meters per second to get the mass in kilograms of the unknown green cylinder. When I put all the numbers into my calculator, I get 0.072 kilograms, which makes sense because if I multiply that by 1,000, I get 72 grams, which if you compare it to the 50-gram mass on spring 1 and you look at what the displacement is for the 50-gram mass and the size of the green mass versus the size of the 50-gram mass, that kind of makes sense just in when you put it in context. So I'm happy with this answer, and I'll let you do the other two problems. You can do this, you can use the same spring constant because the spring constant of a particular spring is constant. So now our task is to use Hooke's law, or a rearrangement of Hooke's law, to determine the acceleration due to gravity on other planets. We're going to have to use the other planets part of the simulation, and I'll show you that in just a moment. We know that force equals mass times acceleration from our previous studies in this class. And another way to say that is weight here on Earth, which is a force, is the mass times the acceleration due to gravity. Here on Earth, we know the acceleration due to gravity is 9.8 meters per second. We don't know what it is on Jupiter or the moon, and it's our job in this part of the lab to figure out the acceleration due to gravity if you go to Jupiter or the moon. I'll give you a hint. Jupiter is a much more massive planet than Earth, so based on what you learned about gravity in the last lab, that might give you an idea about the size of this number. The moon is a much less massive celestial body than the Earth, so that might give you an idea of what this number should be relative to gravity on Earth. I'm going to let you figure this one out on your own. You can find the acceleration due to gravity by multiplying the spring constant, which we used in the last problem, and we found in table 1 here. So you can use whatever spring constant you found here. You can find the displacement for 100.1 kilograms, which is 100 grams. So you've got the spring constant, you've got the displacement. Of course, you're going to convert that to meters by dividing the centimeters on the ruler by 100. You're going to multiply the spring constant times the displacement, the centimeters converted to meters, and divide that number by the mass in kilograms, which is right here. So I will let you do that one, and we'll do part 2, harmonic motions of springs, in the next video. Thanks so much for watching. Good luck with the lab.